So good morning, students. So this is Gnanasaravanan sir back again. So with another experiment. So even today we are going to see one interesting experiment. So I'm going to teach you about the theoretical part, and I'm going to teach you about means give demo about the practical session 2. So today's experiment is experiment number 2. So I think we last class we saw about the Darlington pair, frequency response of Darlington amplifier, and before that we saw common collector amplifier, and we started with fixed bias circuit. So we skipped the second experiment, and now we are going to do the second experiment, right? That's because there was a relevance between common collector amplifier and Darlington amplifier. So that's the reason of it. Let's move on, right? So we are on electronic circuits 1 lab component, right? So today's experiment is experiment number 2, frequency response of common emitter amplifier. So why do we call it as common emitter amplifier? Because emitter is will be grounded, and it will be common between the input and the output. Output will be at collector and input will be at base. So any of hope that was made more pretty clear in theory classes, right? So our agenda is to construct design and construct a common emitter amplifier configuration, and to measure the gain, means what's the output voltage. We'll try to plot the gain versus frequency response, and then we'll try to determine what's the bandwidth, right? So the equipments and components that is required is basically the whatever I have highlighted in red. So those are equipments, and whatever is in black, so those are components. So the first major component that is required is BC547. So it's a 3-terminal plastic package transistor, BC547. There is also a metallic transistor which is called as SLR CK100. So that we'll see in some other experiment. Other than that, another major component is a resistor. So we require many resistors, like varying variants: 22 kilo ohms one number, 4.7 kilo ohms one number, and 330 ohms one number, 1.2 kilo ohms one number. So other than that, we need capacitor, 4.7 microfarad one number, and other than this we need a breadboard and wires and so on, right? So why the name common emitter? That's necessary to see. See, as I said, in common emitter and common collector, there is one major difference. The emitter will be grounded, or through a resistor it will be grounded. Where you take the output is going to decide whether it is common emitter or common collector. For example, it's easy to understand. If it's common, here the input is given to the base terminal, right? The output is taken across collector terminal. So base use பண்ணிட்டோம், collector use பண்ணிட்டோம். So which is the one which is left out? It is emitter. So the emitter is common between the input and the output. So that's why you call it as common emitter. On common collector or an emitter follower, output இங்க ஒரு resistance போட்டு எடுத்துருப்போம், right? So where the input terminals is base and the output terminals is emitter, and the unused terminal which is common between the input and the output will be collector. Adanal the common collector. So where you take output is going to decide whether it is common emitter or common collector. So if you take it in collector terminals, if you take the output at collector terminal, it is called as common emitter. Here emitter is common between input and the output through ground. So common emitter configuration is the most widely used configuration because it has a good voltage gain as well as the current gain. The last experimental common collector, you should have seen that the voltage gain was unity. Whatever you gave at the input, you got at the output. There is no voltage gain, but there was a current gain, but we didn't measure that. So whereas in base, common base, the voltage gain will be will be more, but the current gain will be unity. But this guy, common emitter, he passes in voltage gain, he passes in current gain. He has a good voltage gain and good current gain. That's why it's most widely used. Got it? So let's proceed further. So this is the circuit diagram. So wait a minute, right? So this is the circuit. There was a small change. The title was mentioned as Darlington by mistake. So I've changed it. So it's a common emitter amplifier. So you can see that this type of biasing is more familiar, right? So it's a voltage divider bias. So hope you know what is voltage divider. So it tends to divide and the entire available voltage into two parts, and a part of the voltage is given to the transistor or the base, right? So this follows this common emitter configuration which we use today follows voltage divider bias, whereas for the fixed bias circuit it was also a common emitter amplifier, but that used a fixed bias circuit, means you didn't had R2, you had only R1. There is a fixed resistor giving bias to the base, so that's why it was called as fixed bias, whereas this one follows voltage divider bias. So other than this, the input is given through the function generator and the output is seen through the cathode ray oscilloscope, right? So you have a coupling capacitor at the input and the output to avoid DC bias, means DC offset at the input and the output. So you have a collector resistance as 1.2 kilo. So this is the setup. So the procedure is as similar to the previous one. You need to give connections as per the shown circuit diagram previously. Then you need to set the input voltage. So note it down. In today's experiment, the input voltage is going to be 20 millivolt. 20 millivolt, like the first experiment. Today also the input voltage is going to be 20 millivolt, right? So after fixing that, we are going to change the input frequency. Voltage is not being changed, and we'll see the output voltage, what is V naught at the collector. So that's what we are going to do. So we'll start it from 200 hertz and we'll go till 2 megahertz or 3 megahertz, something like that. Then we'll try to tabulate the reading, we'll plot the graph, and we'll see what's the gain. So, right, so that's the idea of today's experiment, right? So we'll find the 3 dB bandwidth. So today's model graph comes in this way. So it's very familiar. It would be like the first one. So first one, listen, ade model graph tha iduko, because that is also common emitter amplifier. This is also a common emitter amplifier, right? Whereas in the last one, the voltage gain was unity, so you got a single line. Whereas this one, there will be, the gain will slightly increase. It will be constant over a range, and then it will tend to decrease, right? So that's how it is going to be, right? So let's uh, move on. So this is how the tabulation is going to be. This is also a very familiar one. For various frequencies, you will note down the output voltage. Finally, you'll try to calculate the gain. As I told before, gain doesn't have any unit, but to have a unit, you go with a decibel scale. So when you go for decibel scale, you'll try to use 20 log of. Else it is gains, formula is V naught by VIN. The input voltage is 20 millivolt, note it down. While doing it, we'll tabulate what is it, right? So it's time for us to go and to do it and to learn how it is. Move on to the workbench, right? So here is our workbench. So the setup is like the previous one. Almost for all the experiment, the setup will be similar, right? So here is a function generator where we use it to generate the waveform. So we're trying to set to means 20 millivolt, right? So that has been fixed, right? So this is regulated power supply, so which is used to give biasing voltage. So I'll try to keep it for 12 volt because VCC is 12 volt. So that's what I call it as VCC. So VCC is biasing signal. So I have a CRO here, cathode ray oscilloscope, to view the output voltage. So the input voltage we have noted it is 20 millivolt. So this is the tabulation. I have taken the readings for your sake, right? So it runs from 200 hertz, 500, 1 kilo, 10 kilo, 100, 500, 1 megahertz, 2 megahertz. When you see this video, you pass it and note down these readings, right? So the output voltage goes in this way. I've told you, right? So it slightly increases. So it goes to 1.6 volt. Then it becomes 2.4 volt. Then for 10 kilohertz, it becomes 4 kilohertz. It remains in 4 kilohertz up to 1 megahertz. And then it becomes 2 megahertz. So when I substitute this B naught and VIN, means gain is equal to 20 log B naught by VIN. So then I get these values. So 32.97 for 1 volt, that is 200 hertz, then 38.06, 41.58, 46.02 over a constant range, then it becomes
So let's check it whether the readings are true, right? So I'm going to keep some 1 kilohertz here. So now it is in 16, 15, 14, 13. So 200, sorry, it went on so low. Yeah, I've come around 1 kilohertz, right? So let's see what is the output voltage, right? So output voltage should be so let's see it here. Look at here. The value is 1, 2 boxes, and 2.2, 2.4. So number of vertical boxes into per division. So that is 2.4 into 1. So that is 2.4 volt, right? So that's how it will be. Right, for example, I'll put another reading. So 1 megahertz, we'll try to keep 1 megahertz, right? I'll increase the value. So it is 96 kilohertz. I'll try to increase it to, yeah, it comes 1 megahertz. 1 megahertz. So what's the reading? So you see 1, 2, 3, 4 volt, right? So it's around 4 volts. So that's what you have got. So that's how we'll take the reading. So after this, it's as usual, we'll try to plot the values. Let me show the arrangement or the setup, right? So here is the circuit. So the VCC is plus 12 volt, positive terminal is given to collector and also to the base as shown in the circuit, right? To the base through a coupling capacitor, the input is being given. You see, this is the input that comes from function generator. So this is the probe, and you see there is a base resistance going to the ground. There is an emitter resistance here, 330 ohms, and there is an emitter capacitance also, right? So that's here. So the collector, you can see at the collector, I'll show it to you. At the collector, you take a capacitor to the output. So the output is a yellow wire. You can see it goes to the CRO. In CRO, there's the reading, right? So that's how the setup is. So you will vary this and we'll try to see what's the output voltage. So that's how all the frequency response characteristics need to be done. So when you plot this on the graph, so all you get is a similar graph like the first experiment. So in the first experiment, we have showed you how to do or how to draw the semi-log sheet, right? So that's all for today. So hope you understood, right? So if there are any doubts, you can clarify. We'll have a separate session. So until now, we'll wind up the session. So we'll see you on another interesting title. So until then, it's bye from GSF, right? Take care and stay safe.